Welcome back. Let's continue on chapter 11, section 8, power series. What we're going to talk about today is first general form of a power series. So if we have the expansion, the form of Cn x to the power n, summation of n from 0 to infinity, which basically is C0 plus C1 x to the power 1 plus C2 x to the power 2 and so on. This represents a power series where Cn are coefficients of x to the power n. So x is our variable, the coefficient is a constant, that Cn basically is the coefficient of that x to the power. You notice that this is kind of similar to a polynomial, and the only difference is that this has infinitely many terms. It means the x to the power n, there is no specific limit on the degree of the polynomial, and can go up to infinity. And if you're dealing with a series, depending on what the x value is, it could be divergent or convergent. So generally speaking, this series could represent a function. Let's call it f of x, but that is a function if for the x value we have a convergent series. So we say the domain of that function is all those x's that the series is convergent. If it's divergent, then it doesn't represent value. Okay, so here, for example, if we're looking at the series x to the power n with the coefficient 1 everywhere, so cn's are chosen to be 1, then what we have is basically 1 plus 1x plus 1x squared plus 1x cubed and so on. This is, if you remember, this is a geometric series. So it's, and a0 of the series was 1, the ratio in this case is x, the common ratio. And we knew that the geometric series is convergent if the ratio is less than 1. So in this case, if x is absolute value of x is less than 1, then we have a convergent series. That means this represents a function if absolute value of x is less than 1. And it turns out we can calculate actually what is the specific function in this case. Maybe I can show you. If you remember, if we have a summation of a0 r to the power n from 0, let me change it to k from 0 to n, then this would have been simply a0 r to the power n minus 1 minus a0, or I can factor out an a0, write it out here, r to the power n minus 1 divided by r minus 1. If you remember, this was the geometric form, or you can write it the other way as well. This is the same thing, 1 minus r to the power n plus 1, not minus 1, plus 1 divided by 1 minus r. It's the same thing. So in this case, what we have is r is given as x, because at every step you multiply an x. From this term to the next one is multiplied by x, multiplied by x. So, and a0 is simply 1. And now here's the difference. As n approaches to infinity, what happens to x to the power n? If we know what happens to the x to the power n, so what happens to this term? We know that if absolute value of x is less than 1, then this number is getting multiplied by itself and it becomes smaller and smaller. So x to the power n, in that case, would approach 0. That's why this is required to have a convergence here. So what happens? It means this basically becomes a0, 1 minus x to the power n plus 1 divided by 1 minus x, and as we know, a0 is 1, so you have 1 times 1 minus x to the power n plus 1 divided by 1 minus x, assuming that n is approaching to infinity, because this upper bound is approaching to infinity, so this term approaches 0, this term approaches 0. So basically what you get at the end is 1 times 1 divided by 1 minus x. So this is a representation of that power series. Or you can say this function could be represented as that summation. They're equal to each other. And this is only true if x is chosen less than absolute value of x is chosen less than. Okay. So this is kind of a relationship between the function and that power series. Okay, so here we'll define definition of a power series. The power series has the form of summation of Cn x minus a to the power n. In the last example that I mentioned here, in this definition, it was only x to the power n. But you can change that to x minus a. So it means you change the center of the series. Okay, so this is exactly the same as saying series C0 plus letting n to be 1, C1 times x minus a, C2 times x minus a squared, and so on, C3 times x minus a cubed. And this is a power series that is centered. In this case, instead of being centered at 0, if you let a to be 0, you will get the earlier definition. Now this one, if we center it at a, this is how you write it, Cn x minus a to the power. Or sometimes they call it power series about a. Okay, so if they say power series about a, or they say power series centered at a, that's what they really mean. Okay, a is a constant, a is fixed. Okay, so now let's look at this and say for what values this series is convergent. So we want to first figure out for what value the series is convergent, then we can talk about, okay, what would be the result of this series, or maybe we can express more information, extract more information from that series. Okay, so for what values of x the series is convergent? If you remember, we had a convergent series. You test for the convergent series. Ratio test was a good test, generally speaking. So what is the terms of the series? Oh no, an term of the series is basically n factorial x to the power n. So n factorial x to the power n. What would be an plus 1? It would be n plus 1 factorial x to the power n plus 1. So if we knew that the series is convergent, then we looked at the ratio of an plus 1 divided by an. And what is this ratio? This ratio could be calculated. We don't really need the absolute value in this case because we know it's positive, but let's keep it because we don't have any information about x. So we have an plus 1, which is n plus 1 factorial multiplied by x to the power n plus 1 divided by n factorial x to the power n. And if we simplify, remember n plus 1 factorial divided by n factorial, that's simply n plus 1. And x to the power n plus 1 divided by x to the power n, that is simply x. Okay, so now ask yourself, when did we know that the ratio test gives us convergency of a series? It was true that this, so we know the series would have been convergent, is convergent if the ratio is less than 1. If this absolute value of n plus 1 times x was less than 1. If it was greater than 1, then we would have said divergent. So when do we get this ratio to be less than 1? When we get x, absolute value of x to be less than 1 over n plus 1. Divide everything by n plus 1. Since it's positive, we don't really need to worry about the absolute value. And as we let the n approaches to infinity, what happens? The absolute value of x must be less than 1 divided by infinity, which is basically 0. Because n approaching to infinity, this term approaches to 0. So it means the only time that we have convergence is that x is less than 0. Or you can say x is exactly 0 in this case, because if x is 0, then we have this terms to be 0, and sum of all the zeros would be 0. So here you can say the series is convergent if x is exactly 0. There is no other option. If x is greater than 0, then that's not possible. If x was greater than 0 here, then you would have divergence. But if you choose x to be 0, then What do you get inside this series? You'll notice that these terms, they all become 0. Sum of 0 always is 0. That means it's convergent. So for what value of x this series is convergent, you can answer that this is x only can be 0. There is no specific interval. It's just specifically one number. Let's try another example. For what values of x does the series convergent? The series of x minus 3 to the power n divided by n. And what you notice is the center of the series in this case is 3, x minus a. A is chosen to be 3. So this is a power series centered at 3. Okay, so let's see. Again, try apply a ratio test. An is given x minus 3 to the power n divided by n. Figure out what is an plus 1. N plus 1 would be x minus 3. I'm not changing anything about the x. It is n is changing to the power n plus 1 divided by n plus 1. Right? So now I'm looking at the ratio of an plus 1 divided by an, and then at the end I'll let n approaches to infinity, so I can make my decision when the series would be convergent and when it would be divergent. Okay, so in this case what we have is, this is an plus 1 would be x minus 3 to the power n plus 1 divided by n plus 1, all divided by x minus 3 to the power n divided by. And if we simplify, you can cancel out the x minus 3 to the power n with this x minus 3 to the power n, and what you have is 1 x minus 3 left. So you have x minus 3 left, and if you move the n to the numerator and n plus 1 to the denominator, this is what we will end. Okay, so now ask yourself, what is x minus 3 less than 2? So, sorry. This is what we end up with the ratio test. And we know now that if this is less than 1, then we have convergence. Right? This is the case if the ratio test was less than 1 as n approaching to infinity, then we had convergence. So what we do is we kind of say, okay, let's figure out when do we have this to be less than 1. And then you can say absolute value of x minus 3 must be less than multiplying n plus 1 and n on both sides. Since it's positive, it doesn't change anything. These will cancel out because they're always positive. So what you get is x minus 3 is less than n plus 1 divided by n. Now, if n approaches to infinity, what do we have? Then absolute value of x minus 3 would be less than n plus 1 divided by n approaches to simply 1. Okay, I can write this limit n plus 1 divided by n as n approaches to infinity, and this is simply 1. So what do I get is x minus 3 must be less than 1. Absolute value of x minus 3 must be less than 1. So I can say the series is convergent if absolute value of x minus 3 is less than 1. This number here, this is normally called the radius of the convergence. Okay, so this is, most of the time they write it as r. Absolute value of x minus a less than r, that means this is the radius of convergence. And if we open up this interval and write it as x minus 3, if you remember, is less than 1, greater than negative 1, this is how you deal with solving inequalities. So if you have this inequality, x minus 3 less than 1, this is the same as thinking about x minus 3 between 1 and negative 1. And if we add 3 to both sides, this would be the same as x being between, add 3 to both sides, that becomes 4. 3 minus 1 becomes 2. So now I can say x is in this interval 2 to 4. Okay, this is kind of the interval of convergence. At the moment, I'm just kind of glancing over the boundaries. These boundaries could be sometimes bracket, sometimes interval. I just want to shortly introduce it at the moment. We will get more focused on it later. So this, and the answer for this question would be, for what x values? If the x values range between, if the x minus 3 is less than or equal to. Okay. Sometimes the boundaries could be bracket or parentheses. I'm not going to mention that for the moment. We will get to it in a bit. Okay, let's try another example. Find the domain of the Bessel function of order 0. So this is kind of a Bessel function, if you might need it in Calc 3. So you just want to introduce it. And has this kind of complicated format. There's a gamma function, basically the general form, but for 0 you can simplify this factorial. So again, if you want to look to see where this series is convergent, you just need to look at the ratio test. What is an? An is negative 1 to the power n, x to the power 2n, divided by 2 to the power 2n, n factorial to the power 2. And what is an plus 1? An plus 1 would be negative 1 to the power n plus 1, x to the power 2n plus 1, which if you multiply the 2 to it, it just becomes 2n plus 2. Be careful with that. I'm replacing n with n plus 1, 2 distributed to it, it gives us 2n plus 2. And you get 2 to the power, similarly 2n plus 2, and times n plus 1 factorial, the whole thing squared. Okay, now let's do the ratio test. An plus 1 divided by an, and you can kind of calculate the limit if you want as well. Now here, maybe I can do that as well, so we can see it, that you can calculate the limit as you go on and approaching to infinity. An plus 1, since we've done enough example already. Okay, so this becomes limit. Okay, what is an plus 1? An plus 1 is this term divided by the other one, so you get, I'm trying to, okay, let's make it write it, negative 1 to the power n plus 1 times x to the power 2n plus 2 divided by 2n plus 2 n plus 1 factorial squared, and all divided by, let me write the fraction this way, all divided by negative 1 to the n x to the 2n over 2 to the 2n n factorial squared. And if we simplify it, we can kind of get rid of the negative 1, and you can cancel out these with the absolute values. They will disappear. There is a negative left, but the absolute value of it doesn't really make any difference. So this absolute value kind of gets rid of the negative for us. And x to the power 2n, you can cancel out this x to the power 2n. Choose different color. You can cancel out the x to the power 2n's. You can cancel out 2 to the power 2n's. There is still 2 to the power 2 and x to the power 2 left. You can factor out n factorial, and what is left is just n plus 1 times n plus 1. So what you have at the end is limit n approaching to infinity. In the numerator we have x squared left, and then there is a 2 to the power 2, which is 4, multiplied by an n plus 1 squared. Okay, so this is what is the simplified form of that. This fraction simply turns out to be this. Now, here's the good part. If we let n approaches infinity, what we get is limit. Okay, let me write it this way so you can see it. 1 divided by 4n plus 1 squared times absolute value of x squared, which is still x squared. As n approaches to infinity, what we have is this term simply becomes 0. So this is 0. So this is 0 times x squared is still 0. And what we can say about that? This is the limit. And if you remember, if the limit is less than 1, we always have convergence. Convergency for what? Convergency for the series. So what this means that for all x, the series is convergent because the limit is always 0. So the interval of convergency is negative infinity to infinity, or you can say the radius is also infinity. Okay, so now here we get to that interval and the radius that I kind of mentioned earlier. Just I wanted to discuss it before we get there. So here, a general form. This theorem is nothing new, so we have talked about this. So if you're given a power series centered at A, so this is a power series centered at A, there are only 3 possibilities that can happen. First one is the series is convergent only for one point, and that's what we did in the first example. We saw that it's convergent only if x was 0. Second possibility is that the series is convergent for all x. This is this last example that we discussed. And the third possibility, maybe I should have wrote it in order, but the third possibility is the difficult one. Is that is some r's, some x's that are that x is convergent for, and for some x's it's not convergent. And you can bound those x's kind of by a radius r. That's what we mentioned in the second example, that the radius was simply 1. Okay, so if there is a positive number r such that the series x minus a is less than r, then we can say r is the radius of the convergence. Okay, and as I mentioned, when you write it and you say, okay, x minus a, absolute value of it is less than r, basically you would say x minus a is less than r greater than negative r. Then you add an a to both sides and you can solve it, and you say, okay, x belongs to r minus a and r plus a. This is what we call the interval of convergence. And here's the issue again. These don't need to be always parentheses. They could be brackets. It could have different format. There are 4 options. It could be something like this: bracket, parentheses. It could be bracket, bracket, or bracket on the other side you would have parentheses, or you can have both parentheses. Okay, and I can show you an example just to see. But this is called the interval of convergency. So there are 4 options that happens. You have to check the endpoints to see if they're convergent at the endpoints or not. Okay, so let's look at these examples. Find the radius of convergent and also the interval of convergence. So there are 2 examples. I wrote 2 examples just to focus on. So we focus on the interval as well. Okay, I'm gonna dedicate the left side to this series on the left and the right side of this space for the other. Okay, so the first example, we have summation of negative 3 to the n, x to the n divided by square root of n plus 1. So I have an equals negative 3. It's exactly the same steps, x to the n. First, you find out the radius of convergence, if there is n, an plus 1. If there is not, then you don't have to deal with the intervals and stuff. If it's all the possible numbers, so there is no interval, it's just from infinity, negative infinity to positive infinity. So let's see. Here we have square root of n plus 2. Okay. Now let's calculate the limit. Absolute value of an plus 1 divided by an as n approaches to infinity. So limit of this term divided by the other one. I can kind of simplify it as I write it because I don't want to take too much space. But if you do the division, n approaches to infinity. This term divided by that one, negative 3's will cancel out, so you'll end up with 1 negative 3. Multiply by x to the power n divided by x, you'll get only 1 x left, and then you would have a square root of n plus 2 in the denominator and multiply by square root of n plus 1 in the numerator. This is what is the simplified form of an plus 1 divided by a. And as we let n approaches to infinity, what we get is limit this ratio are containing the only terms containing it. That ratio simply becomes 1. As n approaches to infinity, square root of n plus 1 divided by square root of n plus 2 is simply 1. You can use Hopital rule for that. So what I'm saying is the limit, okay, maybe I can write it so you can see limit, you would have square root of n plus 1 divided by square root of n plus 2 multiplied by negative 3x, or you can just simply write 3x. The absolute value makes it positive as n approaches to infinity. What does this simplify to? This is the part that contains n. That's why I took it out. This part simply is 1. So what you have is absolute value of 3x. And when do we have convergency? We have convergency if this is less than 1. So what can I say about x? We know that the absolute value of 3x must be less than 1. So x must be less than, absolute value of x must be less than 1/3. So I found out what is the radius. The radius of convergency is 1/3. This is the radius. And what is the center, by the way? The center is 0. This is minus 0. So the center is 0. And how about the interval of convergency? Now here is the important part. Scroll down a bit more. Okay, so the interval would be x between 1/3 and negative 1/3. This is how you write the absolute value. Or you can write it as x is in negative 1/3 to 1/3. So the issue is now, what are these endpoints? Is it bracket, parentheses, parentheses, bracket, bracket, parentheses, parentheses? So this is the issue. We just need to figure out what are the endpoints. So I'm going to focus on what happens if x is negative 1/3 or 1/3, and discuss, are they going to be convergent? If x is negative 1/3, is it going to be divergent? Depending on that, I'll choose the bracket or parentheses. So let's first pick x to be negative 1/3 and see what happens. So I'm assuming x is given as negative 1/3. So what do we have as the series? The series, you go back and replace negative 1/3 for x. I'm replacing x with negative 1/3. So what we get is series becomes summation n from 0 to infinity, negative 3 to the power n, and instead of x I replace negative 1/3 to the power n divided by square root of n plus 1. And if we simplify, you can see that these two will cancel out. They're both opposite of each other. So what you end up with is this series, n from 0 to infinity of 1 over square root of n plus 1. And what is that? That is simply, this is simply divergent. Why is that? Because the denominator would have, you can compare it with using comparison test. If you remember, the denominator should have a degree of at least 2. At least then comparing with the p series 1 over n to the power p, this p must be greater than 1, but here is n to the power 1/2. So this is a divergent series. So I can say, okay, x, as if x is chosen negative 1/3, then I have a divergent series. So at negative 1/3, I'll use a parenthesis. So negative 1/3 is not included. What if we chose x to be 1/3? What happens in that case? If x equals to 1/3, then the series simplifies to n from 0 to infinity. You'll have negative 3 to the n, 1/3 to the n, and divided by square root of n plus 1. And this simplifies to summation. The 1/3 and 3 will cancel out, so you end up with -1 to the n divided by square root of n plus 1. Here's now we should still remember a bit more about what we know about alternating series. By alternating test, alternating series test, as n approaches to infinity, this term, the an approaches to 0, so an approaches to 0, as n approaches to infinity, and we have a decreasing sequence. So what we know is this is a convergent series. That means if x is chosen to be 1/3, then we have a convergent series. So I can say this interval must be bracketed 1/3. Okay, this is how you deal with the endpoints. So every number between -1/3 to 1/3 and the endpoint to 1/3 is acceptable to have a convergent series in this case. Okay, how about the other one? We do exactly the same idea. So let's see what is an plus 1. First an is chosen to be n x plus 2 to the power n divided by 3 to the power n plus 1. An plus 1 on the other side would be exactly the same thing. Instead of n, replace n plus 1. So you have n plus 1, x plus 2 to the power n plus 1, and divided by 3 to the power n plus 2. Instead of n, just replace n plus 1 every. And then calculate the limit. What is the limit as n approaches to infinity of absolute value of an plus 1 divided by an? And if we calculate that, this is the limit. Again, I'm going to skip ahead a bit. You can do the divisions and simplification yourself. This x plus 2 to the power n and x plus 2 to the power n will cancel out. 3 to the n plus 1 and 3 to the n plus 1 will cancel out. There is 1 3 left here when you do the division. And so what you have is n plus 1, x plus 2 to the power 1 divided by 3n. This is what is left at the end. And as n approaches to infinity, what happens? Again, you can write them, the terms containing n, you can write them outside. N plus 1 divided by n, x plus 2. I can write the 3 out here as well, just to make it easier as n approaches to infinity. You cannot add the 2 outside. Be careful with that. I'm just taking out the multiplication part. This is multiplied. These terms are multiplied. Since they're always positive, I can write it outside the absolute value. This kind of simplifies to that ratio is 1 as n approaches to infinity. So we have 1/3 absolute value of x plus 2. And when do we have convergency? We have convergency if this is less than 1. That means 1/3 absolute value of x minus plus 2 is less than 1, which means absolute value of x plus 2 is less than 3. Multiply both sides by 3. So what is the radius of convergency? 3 is the radius of convergence. So this is the radius. Okay, how about the interval? Again, the interval becomes x plus 2 is less than 3, less greater than -3. Subtract -2 from both sides, subtract 2 from both sides. What you have is x less than 5 and 1. Or you can write it as, I shouldn't have erased it, sorry about that, x plus 2 less than 3 greater than -3. This is the same as saying x is in, add -2 to both sides, all three sides. X would be from -5 to 1. And again, you don't know if these are parentheses or brackets, so we have to check the endpoints. And how do we check the endpoints? We let the x values, either x would be -5 or x would be 1. In both cases, we check for the convergency. If x is chosen -5, what do we get? Let's replace it into the series and replacing x with -5. So what we get is summation n from 0 to infinity n times Negative 5 plus 2 becomes negative 3 to the power n divided by 3 to the power n plus 1. And this is equal to summation. Simplify it. N from 0 to infinity. 3 to the n and negative 3 to the n will cancel out, so you'll end up with negative 1 to the n. You can take out the negative, and then you have 3 to the n divided by 3 to the n. So you can cancel out that and say n divided by 3. This is what is left. And what do you notice? This is always divergent. As n increases, this series, the terms are becoming larger and larger, so we have a divergence. You can use the alternating test, or you can just say an does not approach to 0 as n approaches to infinity. So we have a divergent series. So if this is divergent for x equal to negative 5, so I'm going to use parentheses. What if x was 1? What happens in that case? If we replace 1, then what we get is summation n from 0 to infinity, n times 1 plus 2 is 3, 3 to the power n divided by 3 to the power n plus 1. And you're going to see the similarity here, n divided by 3, n from 0 to infinity. Again, now, this is our an. This series is divergent since an is increasing, since an, which is n over 3, approaches to infinity as n approaches to infinity, So we have a divergent series at this point as well. So what does it tell us? It tells us this interval also has to be parentheses on the right side. So it could have double parentheses, double brackets. This is so there are 4 options that may happen. You have to check those endpoints. And this is kind of the end of this section. You just need to figure out where is it convergent, then later on we'll talk about, okay, now can we do more with this. Okay, so I'm going to stop at this point, and next time we will continue about representation of function as power series.